Preprocessing few continuous variables. Hi. First, let's make sure all our continuous variables are numeric. Going through the list with variable types the info method gave us, we can see employment length and term of the loan we mentioned in last lecture. We expect them to be numeric, but they are rather objects, that is, the pandas data type for text strings. In order to be able to assess what needs to be done, we can apply the unique method to the employment length variable and display the values it takes. There are 10 years or more, less than 1 year, and then all the values from 1 to 9 years. Of course, there are some missing values too. In fact, the values are stored as text because we've got the word years at the end of each. For the most part, to turn each of them into an integer, we have to get rid of the years string. Moreover, for some of the values, there are some other strings we will need to get rid of. Strings like plus years from 10 plus years, and less than and the singular year from less than 1 year. When using data frames in Python, as well as in some other popular data science environments like R, we can apply operations to all rows of a certain column. We can replace or delete certain parts of the strings contained in all rows of the employment length column. Besides, there is a method called str.replace that allows us to search for a string inside another string, and if found, replace the first string with a given new string. The str.replace method has two arguments. First, the string it is looking for inside the string it is applied to, and second, the string it is going to replace it with. Of course, if the first string is replaced with nothing, it will be deleted from the given string. We can easily apply this method to all entries in the column employment length. Nevertheless, we have to be very careful about sequence in which we do that. Imagine we first replace the string year with nothing, that is, delete the string space years from all strings. This will work quite well for the values from 2 to 9, but won't affect less than 1 year because it won't find space years in it. It will also cause 10 plus years to become 10 plus, which is not an integer either. So when applying operations like that, the sequence in which we are searching and replacing strings is of major importance. Okay, now let's store the preprocessed employment length variable in a new variable called employment length int, where int stands for integer. We can use the following sequence of searching and deleting the unnecessary text strings. First, we assign the new employment length int to be equal to the employment length variable with the string plus years replaced with nothing. This will only affect the rows with values 10 plus years from the initial employment length variable, making them 10. For now, all other rows of the new employment length int variable will have the same values as the rows of the initial employment length variable. Next, taking the newly created employment length int variable, we can replace the whole string less than 1 year with the string 0. Then we can do the same with the NA string, replacing it with the string 0. Only now can we replace the string space years with nothing, and finally replace the string space year with nothing. After executing the sequence of replacements, we are left with a variable which is of the object data type. We can check the data type of a single element, say the one with the 0 index, to confirm that. As you can see, it is still the string. To transform emp_length_int to a numeric column, we can use the pandas function pd_numeric. Let's check what the data type of the first element again. Great, it is float64, a numeric variable. Another variable requiring a similar treatment is term. However, we'll leave it for you to exercise as a homework. We will do that a lot during this pre-processing part, so please pay attention while we show the operations and practice them afterwards. Great! Now, take a look at two other variables, date of earliest credit line and loan issue date. These are string variables, but are actually supposed to be date variables. What we can do with them is calculate the time that has passed since each of these events, time since the earliest credit line was issued, and time since the loan was issued. In this lecture, we will calculate the number of months since the earliest credit line was issued, while leaving the number of months since the loan was issued for homework. To begin with, we can examine the earliest credit line variable. It contains records composed in the following way: the first 3 letters of a month, followed by a hyphen, followed by the last 2 digits of the year. All values are strings. As we already mentioned, in order to calculate the time since the earliest credit line was issued, we need some measurement of time, rather than a string. So our task will be to turn the strings into timestamps. There is a dedicated pandas method called toDateTime. It turns an input string in a timestamp, but requires that we specify the format of how the string represents time. In our case, we will need to inform pd.toDateTime of our observation that the time is represented by the 3 first letters of a month, followed by a hyphen, followed by the last 2 digits of the year. We can do that with the expression %b-%y. Let's break it down. %b is a specific way to instruct pd.toDateTime to look for the first 3 letters of the month in the string. Respectively, %y is a way to instruct pd.toDateTime to look for the last 2 digits of the year, and the two are separated by a hyphen. If you are unsure of these syntactic peculiarities, you can always refer to the pandas documentation. Okay, let's save this result in a new variable, earliest CR line date. By checking its type, we confirm it is indeed a timestamp variable. But we're not done just yet. We have created a timestamp. However, it is not enough. In fact, we need the time since the earliest credit line was issued in order to use it in a regression. We have the date of earliest credit line issue. Now we should set a reference date to calculate the time that has passed. For instance, we can take today's date, and that's what we often do in practice. But since our data is older, let's assume it's December 2017. Here, we'll use the same function, pd.toDateTime, and we'll supply the string 2017-1201 to it. In this particular case, we don't need to specify the format because this is the default format that the function is expecting. From this date, we subtract the values in the earliest credit line date column. Excellent! The result is the number of days between the time the earliest credit line and December 2017. Conventionally, we prefer working with months. We can easily do that by dividing by 30, for example. However, a better and more precise way to do it in Python is to get the difference in months. We do that by dividing by the expression np time delta 64 brackets 1 m. This expression converts the time difference in the number to months. We'd also like to get whole numbers, so we round the result, using the round method. Finally, we'll store this result in a new variable called months since earliest credit line. Awesome! Let's explore what's inside. The describe method shows us some descriptive statistics like mean, standard deviation, minimum, maximum, and some quartiles. Everything seems fine, except for the minimum value, which is negative 612. It is impossible to have a negative time difference between a time in the future and a time in the past. That's why we need to further explore and solve this issue. We can start by displaying the data points where the negative time differences were calculated, together with the earliest credit line variable we created. We can select specific rows and columns of a pandas data frame by their labels with the lock method. So let's type loandata.lock. In the brackets, we need to specify which rows and columns we want to slice. We want all rows, and we specify that by typing a colon. We separate the rows and columns with a comma. The 2 columns we are interested in are earliest credit line date and months since earliest credit line. In order for the expression to be interpreted correctly, all columns we want to see need to be given in a list. Thus, the sequence of the names of the two columns has to be enclosed in brackets itself. We wanted to see only the observations where our calculation of months since earliest credit line resulted in a negative number. So, on top of our selection, we have to apply an additional restriction. Here, in brackets again, we specify we want only the observations where the variable months since earliest credit line is less than 0. Great! It seems that there are rows where months since earliest credit line is negative. In the earliest credit line column, we can see that for all of these rows, the earliest credit line date is way into the future, after the year 2060. Most likely, what has happened is that when we were turning the strings into dates, variables ending in 60-something were not interpreted correctly and were turned into year 2060-something instead of 1960-something. If this hypothesis is true, the best way to solve this would be to turn those dates to the actual 1960 dates and recalculate the difference. However, this process may be difficult and time-consuming. Most likely, the issue arose in the first place because the origin of the built-in timescale starts after the 60s, perhaps with the year 1970. On the other hand, we can argue that since we have more than 880,000 observations, we don't need these. Removing them from the analysis won't impact our conclusions. But data is very important for us, and we don't like removing them so easily. In such cases, it is best to choose an approach that is somewhere in the middle between those two. Since we need the difference in month between the date and the earliest credit line was issued and December 2017, we can input values directly into the months since earliest credit line variable. But what values shall we impute? Well, we know that we get the negative values for credit line issues at a very distant point in the past, in the 60s. That is, a longer period than all other credit lines that we normally get values for. So why not substitute the negative values with the maximum observed normal, or positive, difference? That way, even if we don't calculate the exact number of months that have passed since the earliest credit line was issued for those issued in the 60s, we put a very large value, and we still get pretty close to the real picture. So, how do we do that? First, from our data frame, we select only the months since earliest credit line column, and then, from this selection, we select only the observations with negative values. Next, we assign these rows to be equal to the maximum of the months since earliest credit line. Finally, let's check the minimum of months since earliest credit line again. Great, it's 73. We've imputed the value successfully, and our variable is ready for analysis. Good job! We have pre-processed only 2 variables, but we have already seen many of the different techniques used in practice. As homework, you can try performing similar pre-processing to the term variable and to the issue date variable. Thanks for watching.